So I'm going to attempt to explain convolutional neural networks. So this isn't a super technical talk, it's just hopefully going to give you the intuition of how it works and why we use them. And I'm happy for you to jump in with questions whenever. I don't know if you want to raise your hand or something, so because you're on mute. But yeah, fire away with questions. You don't have to wait till the end. Okay, so they are mainly used in image recognition. Is anybody familiar with a convolutional neural network?
I've heard the phrase.
Yeah.
Yeah,
Okay.
but that's
Examples that you may have seen where it's in use is Facebook, where it auto-suggests tags for your photos, and Google when you do a photo search. Those are examples of where it's being used in anger. So, intuition. This is an elephant, and it's obvious to us that this is an elephant. The way we're designed is, we can tell straight away that's an elephant. But unfortunately for computers, that's what they see. And actually this is a simplified version because this is a colour image, so what they'd actually see is a 3D tensor with a layer describing how blue each pixel is, a layer for how green, how red, etc. So it's just a bunch of numbers, and it's really hard to tell how they relate to one another and what it means. To add to the difficulty in, so it'd be very, very hard to code a computer and to be able to do this themselves, especially because these are all elephants and they're all different. So some are close to the camera, some are far away, different angles, different poses, black and white, smiling for some reason,
and jumping.
Jumping.
Well, yeah.
I'm not sure if that's
not real.
But it'd be very, very difficult to code that manually into a computer to do it. So what we do is we construct a neural network so that the computer can learn by itself how to recognise an elephant. So if we were to use just the plain bog standard vanilla neural network, it would be very, very computationally expensive because it wouldn't know that any of these pixels relate to any of the other ones. It'd just be independent numbers, so independent features. So if we had a high definition photo, 1,000 by 2,000 pixels, that would be 2 million features that we'd have to plug into our neural network, and so it'd just be massive and really, really time consuming and expensive. So this is why we use convolutional neural networks, and this is where convolution comes in. So at a high level, what it does is it reduces the number of features that the neural network has to consider by establishing the connections between the pixels and the relationships, and narrowing down to just the most important ones for the neural network to then learn about. Let me just check my notes. Yeah, that's everything there. So just zooming out, this is broadly what it does. So you have your input data. So here we've got loads of pictures of cars, and you put that into your convolutional section of your neural network. And what that does, actually no, I need to go back. I've forgotten something. So what I forgot to say here was, in order to explain how convolution works, we need to think about how we recognise these are all elephants. So what we do, probably subconsciously, is we break down these pictures into smaller bits. So what makes an elephant to us is, well, it's probably, it's got wrinkly grey skin, and it's got long white tusks, it's got big floppy ears and a long trunk. And how do we know that those ears are elephant ears, for example? Well, they're big and they're grey and they're floppy or whatever. So we subconsciously go through this thing where we break down the image into recognisable parts, and then, okay, that makes an elephant. So that is effectively what we do with convolution. So I'll go through in more detail how we do that over the next few slides, but the image gets broken down into smaller and smaller bits until we're left with some really quite simple features. So like curves or lines or darkness or light or smooth or whatever. And the cool thing that I wanted to mention here was that we don't tell it what to look for. We don't say, okay, these things are the things that makes an elephant an elephant. It learns that itself, and it might not be what we think identifies an elephant. It might be something completely different that it chooses. So I thought that was pretty cool. And so that all gets passed through. Then you get a set of features that get passed through a neural network, and it spits out a classifier which has got a probability that your image is one of several output classes, and you can have as many classes as you like. You decide that when you build your network. Yeah, so that's the broad picture. So I thought I'd start with this slide because it's quite a good way to visualise how we perform convolutions over an image. So your first layer in your convolutional neural network is a convolutional layer. And what you do is you apply something called a filter to the image, and you apply it to different parts of the image. And what that filter is effectively a matrix of numbers that describe some quality about the image. So in this example, we've got our input image of a mouse, and this is our filter, and the matrix representation is there. So you can actually see that line in the numbers there. And what we do is we apply that filter to a section of the image, and we do that by multiplying each cell element-wise, and then we sum them all together. And so if I just talk you through this one so you can see how it works. So this is our filter, and this is the segment of the image that we're going to compare it to, and you can see straight away they're pretty similar. And so when we do the multiplication and the summing, we end up with a really big number. And then by contrast, if we're taking the same filter and applying it to this part of the image, they're very dissimilar, so we actually end up with 0. So it's just a way of seeing how similar parts of the image are to a certain quality or feature, and it's actually just a feature identifier for your network. And as I said before, we don't tell it what to look for, it learns what to look for.
So it comes up with a representation as well?
Yeah.
Okay.
Yeah.
And just to help me get my head around it, how does it apply the filter to every single, does it just sort of work its way across the image, or?
Yeah, so actually if I go to the next slide.
Oh, sorry.
Yeah, so I maybe should have put this one before, but yeah, so the way it works, the way it's applied is if you pretend you've got like a torch and you're shining at your image, the square of light that hits the image, that's your filter. It's like this yellow box here, and you move it across the image. It's called convolving, and so you can decide whether you move by 1 or by 2 or however many. That's called the stride, and that's one of the hyperparameters of your network that you can tune. Obviously, the bigger the stride, the less data you're going to get. You lose a bit of resolution there, but you know.
And the size of your filter is another parameter that you feed in as well, right?
That's right. Yeah, exactly right.
I'm sure I've got the terminology right, but yeah. Okay.
No, that's right. So I don't know if you can see here, but the little red numbers in that yellow box, that's the filter numbers that you are multiplying there. And what you get out of that is then a convolved feature map. So this is just an example of one filter, but you can apply many filters, and you will end up with a map that's deeper, so it will become a tensor. It will be several layers deep. And it's good to apply many different filters because they can describe different things. So you get more information. So the next type of layer in your network that you typically have, and you don't have to have this as an optional layer, it will work without this, but it's good to have a pooling layer because what this does is actually reduces the number of features. So the most common way of applying this is to use max pooling, and what that does is it takes a section, so this is your output from the previous slide, this is your feature map, and it takes a section and it just picks the highest number, so in the pink section it's 6 and then 8 and so forth. And that's basically just keeping the most important prominent pixels, the brightest pixels or whatever, the most important ones for your features. So just zooming out again, this is the overall architecture of a CNN. So you start with your input data here, you have a convolution and then typically a pooling layer, and you can have several of those. You know, it doesn't have to be 1 or 2, it can be as many as you like. But you will finish with a fully connected neural network at the end, and then you'll have these predictions spat out at the end.
What does fully connected neural network mean?
Well, actually, on my next slide.
Keep doing this, just keep
These are
practicing.
planned. Yeah, so for those of you who are not like super familiar with neural networks, when we say fully connected, it just means bog standard normal neural network. But what I didn't realise before I started looking into preparing this talk was that the convolutional part is actually just learning features to feed into a neural network. So it's almost like a separate section that you could take off or then attach to a different neural network. So your output from these layers feeds into a neural network. The neural network is sort of modelled on the way a brain works. So you have nodes and connections between nodes. And on these connections you'll have some weights that are applied. So these weights are something that the neural net learns itself. But it's basically, without going into super loads of detail, it's basically taking your input data and learning how to classify it. Sorry, classify it as something at the end. And so what you would typically do is you would have a training data set of, I don't know, several thousand images or whatever, with labels. So you would tell it, this is a cow and this is a cup, for example. So you'd pass those through and it would spit out a probability, and then you would compare that with the label. And the difference between your prediction and your label is your error or your cost. And so the network would then aim to minimise that cost. How it would do that is it does something called back propagation, where you pass back the error through your weights and you adjust them accordingly. And this actually happens all the way through to the convolutional layers. So all the time it is relearning how to classify the features, but it's also adjusting these features each time so that they're more optimal. So I thought that was pretty cool. And and none of this is coded. It's learning it by itself. What I thought I'd finish with, because I thought this is pretty cool. These are actually this is actually real features that a CNN has learned. So it was fed. This is very blurry because it was quite a small image from a textbook, but these are the input images of elephants that were fed into a CNN, and the broken down object parts. And then this is what that neural network learned as features of an elephant. So to that CNN, that is what makes an elephant an elephant. So I thought that was pretty cool.
Mm-hmm.
Yeah. If there's any questions, I'm happy to have a go.
Great. No, that's fantastic. Very good.
How do you make it stop? Oh, there you go.
Great. That's good.